Good day, good day. We meet yet again, and it's so awesome to be with you once more. And just still continuing on that section of electrodynamics. I just thought today I want to just show you just a different example because I wanted to give it as a warning of some of the misconceptions that are there when it comes to electrodynamics. So let's do that together. And by the way, if you haven't subscribed to our channel, please welcome, welcome. You are almost ready to be part of the family. Just click that subscribe button. And then for those of you that may want to get in contact with us, just check our email, okay, on the bio or even on the comment section of this video. Now, so what I want us to do quickly is just look at this question because I saw this in some past exam question a long time ago. I forgot which it was, but I thought let me just do this question with you so that you can understand it. Okay, right now, first of all, they had given us a circuit, okay, and what happens there is that they've connected a voltage source, okay, and they've given us the maximum voltage of that source. Now, I want you to note, ladies and gents, when I give you a source of voltage, this is more like a battery, if you think about it in Ohm's law, in circuits, you know, when we do electrical circuits. But in this case, when they give us a battery like that, okay, just know that it's an alternating current source. So it's as good as a plug at your home or whatever the case may be, right? So it provides us with alternating current. Now, what happens is that we know in this case, now the warning that I want to give you is that please note that this does not in any way deviate to circuits as we normally know it, okay? The fact that this section would be under electrodynamics does not mean that we deviate at all from what we've learned from Ohm's law. And by the way, if you haven't watched any of my videos on Ohm's law on circuits, where have you been? Please just make sure that you watch those videos and you'll be quite proficient at working with circuits or dealing with electrical circuits. Right, now they say to us calculate the power. So obviously, if we want to calculate the power in electrodynamics, which power are we talking about? It's obviously the average power, okay? So this would be dealing with the average power that is delivered by this battery, by the speaker. So it's that speaker there. Now, for most people, because they're dealing with a different section, they'd say, all right, so you are given V maximum. So obviously to calculate the power, what would you need to do? Okay, so deliberately I'm going to show you something wrong that we'd normally do, right? And say, well, of course, to calculate average power, what do I need? I would need to find out what is, okay, I know the resistance of this guy, and I would have V, I can get VRMS from that, isn't it? So VRMS, I'd use this formula that says VRMS squared divided by the resistance. And please, I want you to note, ladies and gents, note that you are given that in your data sheet. You don't need to remember the formulas, but of course, I know you are working hard, you are practicing every day. You should be able to get that quite easily for yourself, right? So please remember, there they are over there. So I'm using this one. Why? Because we've got the RMS, or we can get the RMS, and we've got the resistance. Okay, right. So for most people, this calculation would translate to, okay, so I'd use this, but first I need to get VRMS. So what is VRMS? I know VRMS would be V maximum. You know by now, if you are watching this video and you don't know what I'm doing, you probably haven't watched the previous one. So please just make sure that you do that. So V maximum, this would be 311.12, okay? And divide that by square root. And in this case, that would give us, okay, so that's 311.12 divided by the square root of 2. And that will give me Okay, that's 219.99. So obviously, let me round that off to 220 volts. Okay, so it means that my RMS value for voltage would be 220. This is correct. And so most people would normally go and say, well, I've got my RMS value, which is 220, okay, squared divided by the resistance. Remember what do we want the power for? We want for the speaker. What's the resistance of the speaker? That would be 8 ohms. Okay, and that's what many people would do, isn't it? Okay, now if that is what you are thinking, ladies and gents, please, I want you to note. Okay, let me just to finish it off. 220 squared divided by 8, that would give me 6050. Okay, so imagine this speaker would give us 6,000 watts. Whoa, goodness. Okay, right. Now, ladies and gents, I want you to note, if that was your approach to this question, may I thoroughly disappoint you and say this would absolutely be incorrect. Why? Now, remember in circuits, we said we've got different types of resistors that are connected. How are these resistors connected? Okay, the current that would pass there would be the same current that passes across the 8 ohm resistor, isn't it? So what do we know about those resistors? They are connected in series. Now, what do we know about resistors in series? We know that they are voltage dividers. Okay, so what does that mean? It means that the voltage that is provided here will be divided across those two resistors over there. So there is no way that that voltage there, or the one that we've calculated, the RMS equivalent of it, is just simply supplying this guy only. If they're connected in series, it means that the voltage across the voltage that is provided will be divided across the two devices. So now let's find out specifically what is the voltage that is across the 8 ohm resistor. However, you know what approach I would have? I always want to make things easier for myself. Now, you remember we already found the RMS equivalent of the voltage, right? So what I'm going to do is, would it be possible for me to therefore determine the current that is passing through the different resistors? Now, note, of course I'm given my total voltage and I've already gotten the RMS equivalent of it, isn't it? Okay, so to calculate the current, I would say, all right, it means that IRMS would be equal to, now note, which current would be passing there? Of course, it will be the total current. But if I use VRMS, therefore it would be the RMS current that passes there. And the same current passing here would be the same current passing there. So I would say, well, according to Ohm's law, I is equals to V over R, isn't it? So it will be the total voltage divided by the resistance. Now, remember from circuits, we said voltage with its corresponding resistance. Now, the voltage that I'm given there is the total voltage, isn't it? It's the total voltage connected across these two. So that would be 220 in being the RMS equivalent of it. But now, which resistance corresponds to that total voltage? Of course, it's the voltage across both of them, and they are connected in series. Can you see that? So in this case, that would be divided by 20. So I would say, well, this is 220 divided by 20, okay? And I get there that the current passing through is 11 amperes. I hope you are all with me, all right? So now with current, what do I know about current? I know the current passing across the 12 ohm resistor should be the same current passing across the 8 ohm resistor, isn't it? Okay, so therefore, can I now find my the power that is dissipated there? I know the voltage, and I know sorry, not the voltage, rather I know the current passing there, and I also know the resistance. So now I would say it means that sorry, average power, so P average, I'm going to now simply say, instead of finding the voltage, right, I could just say it's going to be I RMS squared. I know the specific current passing there, multiplied by R. Okay, so I'm using this formula here because I know the current and I know the resistance. So I RMS, this would be 11 squared multiplied by R in this case, which is 8. And note, so that's 11 squared multiplied by 8, and that should give us 968. Sorry, that is P average, so that's 968 watts. Okay, so ladies and gents, I just wanted to give a warning with that. Of course, even if we're to get that for resistors in parallel, okay, right, I won't do that with you, but I'm sure you'd know what to do. What do we know about resistors in parallel? Well, of course, I do know that the voltage would be the same across both resistors and the one that is supplied, but I also know that current divides. Okay, so if you wanted to get the current IRMS for this one, it would not be the same IRMS as the total of that. Okay, right, I hope you get that. For those of you who've watched my video on circuits, I'm sure you would be able to follow on quite well. Now what I want to do in the next question is I wanted to also do a past exam question that involves something that we didn't do in the previous video. Okay, so just stay with me. Let's do the next question quickly and we wrap up. Okay, so I take the 2019 paper. All right, this is DBE 2019. Okay, obviously this, I think it was written in, yeah, that's the senior certificate, national senior certificate. So this was written in May, June in 2019. Okay, you can check that out for yourself. Okay, so there it is there. They give us a that structure there. Obviously, what graph is that? This would be alternating current, isn't it? Okay, so they say, does this, okay, they say the diagram below shows the voltage output of a generator. So they told us it's a generator. Okay, they say, does this generator have split rings or slip rings? I'm sure if you watched my previous videos, my previous video on electrodynamics, you know that for AC, all right, you use slip rings, so it will be full rings like that, whereas for DC, okay, so this would be alternating current, okay, whereas for DC you use split rings. Okay, and I said for you to remember that, all I just simply do for myself is just remember CD is DC. Okay, so you can just use that if you like. Okay, so they say, does this generator have split rings or slip rings? Definitely it's AC, so it must have slip rings. Okay, and then they say, which one of the diagrams, A or B, so these ones over here. Okay, so they've got armatures that are in different positions. Okay, so the one armature, what they've done is they've made it to lie flat like that, and the other one, it's actually at 90 degrees like that. Okay, so they say, which one of the following diagrams, of the diagrams below, A or B, shows the position of the generator coil at time 0.10. So let's check on the graph. At 0.10, can you see that our value there is actually 0? Okay, now ladies and gents, I don't want to go into the nitty-gritty details of it, but let me explain that to you very quickly. So when the armature is actually, now if you think about it, this is the magnetic field. It would be passing almost parallel to how the armature would be sitting. So in this case, it means that the current would be maximum when it's sitting in that position, okay, when you've got your magnets this side and this side, okay. So in this case, it would be at 0 degrees or 180. So in this case, it would actually be maximum, okay. But when it's sitting at 90 degrees like this, okay, that is in that position there, okay. So if you think about it, at that point when it's maximum, it's when the armature is sitting in that position, and then when it's minimum like that, it's at 0. This is when it's actually sitting in that position, okay. Right, so our answer there should be position B, okay. Right, if you don't get that, please, it's 1 mark. It's worth just passing through and then just going to the next question. All right, quickly, what I wanted to do with you there was do the calculations on the root mean square, just to show you that this, guys, is really, really simple. You can be able to get that quite easily, and it's worth just easy marks, okay. Right, so they say calculate the root mean square voltage of this generator. Now, note, what did they give us there? They gave us the maximum voltage. So when they give us a graph, we know we've got the maximum voltage there. And so the RMS, we can just simply say V RMS is equal to V max divided by the square root of 2. And we know this is 312 divided by square root 2. And let's do that quickly. I suspect it's the same as what we just did, divided by square root 2 there, and we get 220, okay, 220.662 if you want to, okay, so that's 220.62 volts, okay. Right, that's our RMS value, okay. And then they say to us, a device with a resistance of 40 ohms is connected to this generator. So we are connecting a device of 40 ohms, and then they say to you, calculate the average power delivered by the generator. So we've got our RMS value, voltage. We've got the resistance of the device, okay. So we want the average power. So we know P average. We're going to go for that formula that has both voltage and resistance, isn't it? So it's going to be V RMS squared divided by resistance. So this is 220.62 squared divided by 40, okay. So I still have this in my calculator, so I'm just going to square that value, okay. And there's the answer. Divide that by 40, and I get 121.6, okay. Oh, sorry, 1216.8 rather. Okay, so 1216.8 watts. Okay, that's my answer to question 9.4. That's 9.4.1. That's 9.3. Okay. Right, and then they say to me, calculate the maximum current delivered by this generator to the device. Okay, so what do they want us to find out? They want us to find out the maximum current. So what you can do, okay, what we can do is, okay, sorry, I'm just going to write in an illogical way there. Let me just fit that there. It would have been better to write from left to right. It's much easier that way. Okay, 9.4.2, but I hope you'll understand nonetheless. Okay, they said they want the maximum current that is delivered. Now, is it possible for us to get the RMS current? Of course. So we say P average. So I would say, well, we already calculated the average power, isn't it? So we can say it's V RMS, which we already have, multiplied by I RMS, which we want, isn't it? So I can say, well, P average, that would give me That's 1216.8. My VRMS was 220.62 times IRMS. Okay, so formula, I've got my substitution, so I can find IRMS. Let's divide both sides by 220.62, and okay, divide by 220.62, okay, and I get a current value. So my IRMS value would be equal to 5.515, or let's say 5.52 amperes. Okay, remember that current is measured in amperes, right? But they didn't ask for IRMS. What did they want? They wanted maximum. So I know IRMS is equals to Imax divided by the square root of 2, and I already have my RMS value, 5.52. Imax, okay, it's what I want. Okay, I'm just gonna move this up a little bit. So that's my Imax divided by square root of 2, and of course we can just simply say Imax is equals to square root of 2 multiplied by our IRMS. So multiply that by the square root of 2, and I get a value of 7.8 amperes. So it means my maximum current would be 7.8. Of course, if you want to know, there could have been another way that you could have calculated this. Okay, maybe let me just feature that quickly. I could have said, well, I already have the power there. Okay, so I could have used P average is equals to I RMS squared times R, because I already have the resistance. My resistance was 40, isn't it? So I could have used my average power and said, well, but I know average power is 1216.8. IRMS squared, I'm looking for IRMS squared multiplied by the resistance, which is 40. Okay, so I can say, well, let's take our power value, 1216.8 divided by 40. But remember, that would give me IRMS squared. So let's take the square root of that, of our answer, and I'm back at that value of 5.52. And of course, once you get there, IRMS, that's 5.52 amperes. And once you get there, you get this. Of course, to get Imax, you'd go back to this formula here. Okay, right. So I just wanted to show you a different way of doing that. And then, ladies and gents, I'm just going to leave it here. This is another way, and all I just wanted to illustrate here is that, this section is quite an easy section. You can really maximize on getting max on this section. Okay, and please, if you haven't subscribed, just remember to do the right thing and subscribe, and tell more people. Come on, tell them you're learning quite a lot. I am determined to just dish out as much good content as possible so that I can help many of you who want to improve your results in order to do exactly that. Otherwise, ladies and gents, thank you so much for lending me an ear. I'll see you guys next time when we do what's that part? The photoelectric effect, rather. So I'll see you guys next time when we do the photoelectric effect, and I hope that you enjoyed the lesson. Otherwise, it's goodbye from me for now. Sharp, sharp.